Hello friends, welcome to the fourth lecture, and in the previous lecture I have discussed different types of vector data. If you recall that I have mentioned that data in GIS can be divided in two major components, one or two major types of data. One is spatial data, another one is non-spatial data. We also call them an attribute data. And then we discussed different types of vector data. Point data, line or polyline data, polygon data. Now in this lecture we will be discussing about what is basically raster data and types of raster data as well. So raster data is having two types, one is the grid type data and another one is the image data. There are not much differences between these two, but still the differences between these two must be understood very carefully, because otherwise while analyzing the data or handling such data may give you some problems. So the understanding about the intricacies of two different types of raster data is very important. We will be also comparing, seeing the advantages associated with vector data as well as raster data. And this we will be doing little later in later part of our lecture. So first the raster data, as you know, that is a continuous data. Vector data I mentioned is a discrete data. So there are just two different way of representing the real world. One, it is in a discrete manner using point, line or polygon, maybe in the tin model, which we will discuss later. But the topic which we are going to discuss in detail is the raster. In a continuous fashion we represent the real world. Now in raster, what are the things which are there, or the key things which are there? That it is a uniform grid. You can imagine that if it is a real world scenario, then a uniform grid is laid out on this. This too, the concept of this too is based on sampling theory, which is called Shannon. Shannon was a mathematician and who gave this theory, which is called Shannon sampling theory. What does it mean here in our GIS parlance is that if you represent a real world in a continuous equal size cell grid, then each cell is representing an average value of whatever present on that part of the earth. For example, if you are having agricultural land within a say 10 meter by 10 meter area, there might be variation in vegetation or say wheat crop or some crop, but everything is averaged down. Say for example greenery or maybe production or anything is averaged down, and one single value is assigned to that cell. That value becomes attribute value of our raster cell. And that is why in case of vector we can have several attributes or theoretically n number of attributes with each vector entity, but with the raster cell or raster pixel we can have only one single attribute. That is one of the major difference between vector and raster. Apart from that, raster is a continuous, vector is a discrete data, discontinuous data. As you can see that the data is stored here in a two-dimensional matrix, which you are having a set of rows and columns. Now number of rows and number of columns need not to be same. As you know in the matrix in mathematics, this is also not compulsory. That means I can have a rectangular size of my data, raster data, or I can have a squared shape. But apart from these two shapes, I cannot have raster in any other shape. However, when we are representing raster for an arbitrary area, then there are some other concept are applied, which we call as no data concept, and by using no data concept on our screen or for our visual, we see a arbitrary boundary for raster, but in fact in the system for the outside area it is stored as no data, and for inside that polygon it is stored the real data. So fundamentally the raster overall shape of the raster will have to be always either rectangular or square, because it is representing mathematically a two-dimensional matrix. Now, each cell, in case of grid we call as a cell, in case of image we call as a pixel. We will see little later all these details. So, each cell will represent one attribute, one value. It may be, in case of remote sensing data, it may be reflection value, it may be emitted value, it may be temperature value, or in normal case may be rainfall value or any other value, but only single value per cell or per pixel. And this cell or pixel becomes the unit of our grid or raster. And another important thing has to remember that the shape of this unit has to be square. So, overall shape of a raster can be square or rectangular. However, shape of a unit has to be always a square, so that we maintain the uniformity. Now, as though mathematician worked on this, and rather than constraining that each unit has to have the same shape, they came with a new idea that instead of square we can have triangles of varied size and shape, and that brought the concept of tin, which we will see little later. So, that the unit of a raster is always a square. Overall shape of a raster can be square and rectangular, and each unit of raster will have only one single attribute, not like vector data. So, raster is a continuous, and we are generally familiar with when we are handling the image raster, then there are image formats like TIFF, JPEG and GIF, and different image processing softwares are having their own format, like IRDAS is having its own image format, which is very popular one is IMG format. So, there are there are the data, this is how it is represented, and then these cells are having. Now, the size of a cell can vary. It is not always 1 meter by 1 meter or 2 meter by 2 meter, but the shape is fixed, which is square, but the size of the cell can change. Larger the area the cell is covering of a raster, we say smaller the spatial resolution, or poorer or coarser the spatial resolution. Whereas a cell, if it representing a very small area of the ground, then we call as a higher spatial resolution. For example, in a satellite image, a 1 pixel might be representing 10 meter by 10 meter, and if we compare another satellite image which might be representing a pixel might be representing an area of 1 meter by 1 meter, that means the image which is having 1 meter cell or 1 meter pixels is having higher spatial, relatively higher spatial resolution. Spatial resolution term is a really relative. For someone, for some applications 100 meter spatial resolution may be useful, but for the another person even 1 meter spatial resolution may not be useful. So, we have to be thinking in this direction, that is a relative term. As per our requirements we call as a higher spatial resolution, or we call it. About the spatial resolution, how different spatial resolution will bring the changes in our image, which we will see little later in this presentation. Now, not only the satellite images which are handled in GIS, but there are other raster data like a digital elevation model, which is representing the undulation or topography of a terrain or part of the earth. That means where are the higher grounds, lower grounds, valleys, hills, slopes, and all those things can also be represented in a form of grid or in raster, and each cell of that grid will be representing an elevation value, and that is why it is called digital elevation model. Example is given here, and here that attribute of that cell of that raster or grid going to be your elevation value. Whereas in case of image, it might be having reflection value or emitted value or temperature value or any other value is represented there. But in satellite images, since this is colored image, therefore it is constructed using three primary colors, and therefore you are seeing in color, but still all are raster and a different type of raster, which is your image raster. So, as I have already mentioned earlier, that there are both both are image and grid, both are the raster model. However, there are differences. In case of image, the unit we refer as pixel, pixel in abbreviation, which is picture element, and the cell, in case of grid, the unit we call as cell. This makes while calling differently also gives us advantage of understanding which is required for the next property or next characteristics, which is the value of the image pixel or value of the cell. In case of image, the value of a pixel can only be positive integer value. We cannot have no other value, and that is another big difference between an image and a grid. Whereas in case of grid, the cell value, that means the unit value, can be either negative or positive integer or real numbers. So, variety of values can go in case of grid data, but in case of image data only positive integer values. So, these two major differences are there. When we say pixel, that means one is talking about image, and once a person is talking about an image, that the unit value of that image, that means the pixel value, has to be a positive integer value. And when I say cell value, that means I am talking about grid, and the cell value can be either positive, negative integers or real values. So, the grid is having more capabilities of bringing or handling all types of integer and real numbers, whereas the image can only handle the positive integer numbers. So, this difference has to be remembered, because if we do not take care about this, then because the format for grid are different than format for image. Image formats we are very familiar, because nowadays we use the digital cameras, and which are also inbuilt in mobiles. Most of the time we are storing images in JPEG, but we can change the format, we can store image in TIFF, and all are these image formats, and that means we are storing pixel values as positive integer values. You can, if you get some time, you can open some image, zoom it and read the value, you would always find a positive integer value. Now, the next thing is which I touched little bit about, is spatial resolution, which is very important to understand, because this is related, though it is a related term, but it plays very important role in our day-to-day life as well as in GIS as well. And if we go by the definition, it is a measure of how closely pixels can be resolved in an image, that is called spatial resolution, and it depends on the properties of the system creating the image. Now, if what does it mean, that if there are two neighboring pixels are there, and if they are having very contrasting properties, they might appear in a particular scale, they might appear separately. So, if you take a digital image, maybe taken by your mobile camera, put it in a computer, zoom it to a very high level, after some time you might realize where the two contrasting things are there, you might realize two pixels or neighboring pixels are showing different colors or shades. So, when you reduce the scale or zoom out, then what happens, that these starts resolving, and then individual boundaries of the pixels you will not see. Now, in our domain, that is in GIS or in remote sensing, this is what we say is the clarity of an image, which is decided by its spatial resolution. That means if an image which is having very high spatial resolution, should be looking much pleasing to eyes, and that means might be that it is having higher spatial resolution. That means the number of rows in order to cover the same area, number of rows and columns are going to be more, and that means the ground area which that high resolution image is representing, that means 1 pixel of that image is representing, is very, very small compared to the image which is having relatively low resolution. So sometimes we, like in digital mobile cameras, we say 10 megapixel, 12 megapixel, 18 megapixel. That means we are talking about the dimension of the image. So larger the megapixel, the clarity of image would be higher, higher the spatial resolution. The example is given here that here the spatial resolution is 110 by 110 kilometer, and you are unable to resolve adjacent pixels, and therefore you are seeing the boundaries of pixels. It is a relatively very coarse image, but when you make this representation is using a finer grid and having a resolution of 30 kilometer by 30 kilometer cells, then at least some clarity has been introduced in this middle stage. But if you improve further and the individual boundaries of 2 neighboring pixels are resolved, then you will start seeing a much more realistic image, and that is relatively having much higher resolution image than the rightmost image. Same thing here, that this is 1 by 1, that means there is nothing, no differentiation is there, 1 pixel only. Whereas here 2 by 2, that means there are total 4 pixels, all are having different colors, but we cannot make out what it is written there or what is what object is within these 4 pixels. But once we start moving and segmenting this area into finer size pixels, an image start appearing. Here in 10 by 10 it appears maybe R, maybe A alphabet, but here it starts appearing as A, R much clearly, but in 50 by 50 and in 100 and 100 becomes much sharper. So the rightmost here is having very high resolution relatively as compared to the first 2, 3, 4 or 5. So this is the major difference with resolution, especially spatial resolution, causes in our representation of raster data, or that might be a grid representing a digital elevation model, or might be a satellite image or photograph taken by your digital camera. Now, as I have already mentioned that vector is a discrete, raster is a continuous model. So now we will try to compare and see what advantages are associated with vector data and what other advantages are associated with raster data. That these data sets are fundamentally completely different, vector and raster. And if a real word has to be represented in these 2 formats, then you can see that if real word is represented, which is a very simple representation of real word here, that you are having a stream, you are having say agricultural land in the background, some forest and a house. If I have to represent that one in the vector, then the house is going an area here depending on the scale. In a smaller scale, that house might appear as a point data, but here is a polygon, and the same with the forest is a polygon, whereas a stream, though in this image it is looking that stream is occupying an area, but here I am representing as a line feature, that means only length, no area. And if I have to represent the same real word into raster, then house will have this much size, 1 pixel is representing house, few pixels are representing forest, and then few pixels or cells are representing the stream or the river here. Now you will realize that I can increase number of nodes in case of vector and can make my line very smooth. But in order to make my line smooth or a stream representation much more smooth, then I need to increase the spatial resolution. That means the representation through my raster has to be with very small cells, and that means I am going to occupy more space on my computer and more handling or processing time if I go for higher and higher spatial resolution. So it depends on your project requirements. All types of nowadays, all types means all variety of spatial resolution data are available. For example, if I take a digital elevation model and I take the example of freely available digital elevation models, then starting from 1 kilometer spatial resolution digital elevation model to up to 30 meter spatial resolution digital elevation models are available. Now, but what is the purpose? If you are going for a small area and you are going in much more detailed analysis, then it is always better to go for higher spatial resolution digital elevation model. But if you are covering a very large area, a large region or a continent, then it is not worth going for a high spatial resolution. It is better to go for relatively coarser spatial resolution, maybe 90 meter, maybe 1 kilometer resolution. So it depends on the requirements of your project and what kind of products which you are going to generate after all analysis in GIS. So variety of spatial resolution digital elevation models, same with the satellite images. Nowadays satellite images of 30 centimeter resolutions are available and satellite images of 1 kilometer resolutions are also available. So again, if you are looking if you are doing analysis on continental scale, then you need not to go for 30 centimeter, because the data handling is going to be very huge and you may not be able to handle data on one single machine using standalone GIS softwares having a very high spatial resolution and data for continental areas. So it is always find out what is the best and then bring in your GIS software and do the analysis. All types of spatial resolution data nowadays are available. Now vector data models, as we know, that it keeps the data either a point, line or a polygon, and which is vector data for certain types of features is good, which are having discrete, but certain types of things which are varying continuously, like for example given a soil, may not be good to represent through the vector data, because soil varies in nature very gradually, not suddenly. But if somebody is using for lithological maps, then we know that lithology changes suddenly sometimes, and therefore maybe vector may be useful in that way. So raster, whereas raster evolved is a continuous data, continuous features, both models are having advantages and disadvantages, which we will see very soon, and the modern GIS are able to handle both types of data models, or rather 3 types of data models: vector, raster and TIN. Another important thing is that GIS are nowadays capable of transforming or converting your raster to vector and vector to raster, however with some limitations. So little later we will be also seeing how we can convert from raster to vector and vector to raster. So if we start looking the advantages first with the vector raster data, this is the most common and very simple to understand. Raster data, easy to perform because mathematically it is just simply a 2-dimensional matrix, and therefore whatever the analysis tools which have been developed in matrix domain of mathematics, all can be implemented easily in GIS. Secondly, all satellite images are also raster, and there are many functionalities, algorithms and every capabilities have been developed in digital image processing softwares, and therefore the same thing have also been implemented into GIS. So raster, because concept wise is simple, and therefore lot of tools are available to analyze the raster data. I have already said about the satellite data, because the satellite data becomes one of the very important data input into your GIS, because it is easily available, it is a continuous data, and with the almost every day you can have some satellite data or another. Whereas the advantages with vector, the biggest advantage with vector is accurate, because even for a house which might be in a small scale map might be represented as a point, but in raster it will have a cell, that means an area. So even a point will have an area, whereas as per the definition in vector, point is a 0-dimensional entity. So raster is not that accurate as vector. Positional accuracy is very high in case of vector data, and it is compact because it is discrete. There is no redundancy in the data. In case of raster, you are having lot of redundancy, and then therefore there are data compression tools are available to remove that redundancy or reduce the size of for storage of raster data. But for vector data, there is no redundancy. Once the topology has been built, then redundancy is completely gone, and no compression, other things are required. So vector data is very compact, and a large area data in vector format can be stored in a small computer space, and can be have as another advantage that in raster you can have only one attribute, but in case of vector you can have multiple. So that is another advantage. As we know that raster, which we have already covered this part, that raster divides into grid cells. Vector uses point line polygons. So units in case of vector are point line polygons, in case of raster either cell or pixel. And this processing can be done with the grid and convert it from vector to raster, and all modern GIS softwares supports all three types of data handling. Raster, as we go finer and finer in the grid cell or pixel size, we go for higher and higher resolution, and the size later on also the size can be changed, but resolution, spatial resolution cannot be in real sense cannot be improved, but from computer point of view you can create more number of rows and columns, and therefore a smaller size cells are there. Now let me take an example of a soil map. As I have said that the soil map, soil is a continuous varying feature, but sometimes we have to represent as a polygon map. So example here is different types of soil maps are represented in a polygon map. But if the same soil map, if I have to represent in a raster, then I have to represent something like that. So both raster and vector representations are there, and what you will see at the boundary line of two soil units, in case of raster you are seeing a stair steps case, or also called edge effect of the boundaries. That means the boundaries are not sharp, and as mentioned earlier, in case of vector the positional accuracy is very high, relatively very high as compared to raster, which you can also realize. So on the edges of two different units, the boundary will have this edge effect or stair steps case, something like stairs which are there. But if you improve the spatial resolution, that if you go for finer spatial resolution, then it might not be that much obvious, but anyway at every stage of raster, at the boundary when it is going in arbitrary, then you will have this edge effect. So that is one of the disadvantages with raster. So finally what I am going to do, I am going to run through all these things with the raster versus vector using different characteristics one by one, and see that what are the advantages with vector and raster. First characteristics which we take is the data structure. By now you must have realized that the vector, because of topology and different types of vectors, relatively vector data is little complex than raster, because raster it is easy to understand, it is easy to handle in computers. So raster is very simple data structure compared to vector data structure, and therefore anything which is simple is much easier to learn. So the ease of learning is also accordingly that vector is having difficult, softwares are complex and expensive, whereas raster one are much simpler. Positional precision, as discussed already, that vector provides very high precisions, and when your data representation is very accurate, precision wise, accuracy wise, then you will have better outputs, In case of raster, the output also becomes little difficult. So precision increase with increased processing time and data storage. Also precision here will also increase with increase of spatial resolution. Now attribute precision, it is very good in case of vector, and you can have n number of attributes associated with each vector entity, point, line, polygon, but in case of raster it is limited only to one entity or one attribute value. Comprehensiveness of analysis capability, it is good for a spatial query with some limitations when it comes for intersections, especially when you are overlaying two polygons together. We will see some examples of such limitations. How these have been resolved in GIS, that we will also see, but still it is limited in GIS. Whereas in case of raster, no issue, no problem, because these raster will stack one of another one thing, and if they are belongs to the same coordinate system and same area, then even the spatial resolution is different, does not matter, they will stack, and you will not find any difficulty while analyzing such raster data layers. The another characteristics which is overlaying ability with the vector is good, but after some time you start seeing splinters. That means lot of polygons will come after overlaying 4 or 5 polygon layers, and interpretation or usage of such maps becomes very difficult. But in case of raster, that problem will never arise. Now storage requirements, as we have already realized that vector require little storage. It is a discrete data, it does not require much storage, and therefore it is though it is complex, but it is easy, it requires less space, whereas raster is simple but it requires more space because of redundancy in the data. And when we will discuss the raster data compression techniques, then we will go in detail how what basically redundancy affects the raster data. Ability to work with the image data, it is not as good because image data is raster, and when you are working with image data and vector data, you will have problems. Whereas if you are having image data is also raster, your grid data is also raster, no problem whatsoever. Conversion to other map projections. Map projections we will discuss in some other another lecture. So when we go for different map projections, vector is very good, and most of the GIS, modern GIS softwares includes change of projection from one projection to another, and if you are having data in vector format, it is very easy to convert from one format to another, one projection to another. But with raster data, it is rather difficult, and it becomes not the accuracy part will also come in between. Now ability to work with the network data structure, because vector data by its because line data, I gave the example that most of these networks like power grid or sewerage line or telephone lines or OFC lines, all are networks, and they are stored in computer or in GIS softwares as vector data, and therefore if you are working in that domain, then it is very good with the vector data, but it is with the raster, obviously it is very poor. Cost, expensive, vector is expensive because each and every node has to be digitized, either by some semi-automatic method, because yet there is no fully automatic method to convert vector data from analog to digital. So maximum the best possible methods are available, semi-automatic methods with the human interventions, lot of human interventions, and therefore the vector data is expensive, whereas raster data is much easier, and that is why lot of free digital elevation models which are in grid format, which is raster, free satellite images are available on net nowadays. So it is not that expensive because in one go a satellite can cover a large area, but it is not possible with vector data. And also the output map quality. Here now vector is having advantage, very good and looks like a map, whereas your raster are poor and does not look like a map. Another problem with the raster data, vector, because a layman or normal people, those who do not know much about GIS, or such fields, they are very familiar with the vector data maps. They have been seeing since very long maps which are having vector data, but people are not very good on seeing or interpreting satellite images or raster data. So that is why many times, though we may be doing lot of analysis using raster data, but then we might, in order to make it is much simpler, we might be converting finally into vector, so that our map quality becomes much good or better, and looks like a conventional map. Otherwise, raster data, those who understand raster data, for them it is no issue. Now I want to cover this about the overlay ability, that I mentioned here that the vector is having limited overlay. So what does it mean here? That if I take example of two maps, both maps are having 3 units each. So here there are 3 units A, B, C, and in land use map there are 3 units 1, 2, 3. This is a very simplest example. In real GIS operations, this kind of simple operations are not performed, many complex operations, and maybe that you might be having not 3 units, maybe 30 units in one map or 60 units in one map. But anyway, in this example, which is a very simple example, attribute, one set of attribute which is for A, B, C, the depth of soil is given here. Whereas in case of land use, which are code are or IDs are for different polygons are 1, 2, 3, and what kind of land use is different units of polygons are being used, forest, agriculture and pasture. When we overlay these one on another using like a transparent sheet, using your set theory concept or Boolean's logic, then this kind of intersection map will have 7 units now in this particular example. So we started with 3 units and we ended up with the 7 units, 7 polygons. Some have become very small, and imagine that if you are having 30 units in one map and say 30 or 40 unit or polygons in another map, and such overlay operations if you perform, then you will end up with hundreds of such polygons, and therefore the interpretation of such maps becomes difficult. In earlier versions of GIS, even overlay of 2 vector polygon maps was not very easy, but nowadays it is not that difficult. So one more field has been added, that means one more attribute has been added, and initially they each has a single attribute, now it is one more, and this ID has also changed. So you are having soil and land use. So A2 is having a part of A of soil map, and second unit or unit 2 of land use map, and likewise you can have overlay even in vector data to certain limits. But if you overlay many polygon vector maps, then you will end up with very small polygons, splinters, and the interpretation of such maps or utility of such maps becomes very difficult. Now I also mentioned that nowadays it is possible to convert from vector to raster and vice versa. However, with some limitations, and whenever you convert from one format to another, one model to another, you will introduce some errors. But only when it is most essential or compulsory, then convert from one format to another. Otherwise, originally if it is available in raster format, keep it as a raster. If it is available in vector format, keep it as a vector, because once you convert from one format or one model to another, you are bound to introduce errors. Errors are inevitable, and as mentioned in previous lectures, that error propagates in GIS. So our aim should be to keep the errors at their minimum level. Anyway, so if I want to convert from vector to raster, what I need to determine, I need to have the row number and column number, and that is what here is L and E. L is the line number, E is the element, that means the column number, and these are the two functions F1 and F2 which are polynomial functions. So again mathematical concepts are coming. Here again polynomial equations are used not only in the conversions, later on extensively polynomial equations are used in georeferencing as well. So, when we will discuss, we will go through different orders of polynomial equations there also. And so, here the input are x and y from your vector data, which are your coordinates, and using polynomial functions you will get line number and row number. Similarly, in case of raster to vector conversion, which is a just reverse, that we need to determine these two coordinates, a pair x and y. So, again there are polynomial equations, and L and E, that means line number and row number, will go as input. And this is what it is, that the line is a scan line or line number, E is the element or pixel, x is the horizontal coordinate in the map projection, y is the y coordinate or vertical coordinate, and f1 to f4 are polynomial functions. So, this is how the conversion from one model to another model is possible in GIS. But as I have mentioned, any conversion is not fully transparent. That means it is going to bring some errors, because you know that now you know that vector and raster data models are two different contrasting data models, and therefore you are bound to have problems when you convert from one to another format. And this brings to the end of this my presentation. Thank you very much.